Hi everyone, my name is Emerald Trong. I'll be presenting my research on strengthening ASIC security through dummy transistors. Before I kind of go into what are transistors and what is dummy transistors, I kind of want to introduce what exactly is ASIC. Kind of go into what are transistors and what are dummy transistors. I kind of want to go back to the baseline. What is ASIC? ASICs are specialized computerized chips engineered for maximum efficiency for a single task. An example is, what if in your smartphone there's an ASIC that is responsible for encryption for your data? They form the backbone of many industries such as finance, healthcare, and national defense. As a critical part of many industries' infrastructure, they're increasingly becoming a prime target for these cyber attacks. So I'll kind of explain the two images. Below is kind of where you can see like the circuits within the ASIC, and each of those circuits can be responsible for one single thing. I kind of mentioned encryption for one thing, but it can be meant for many things. On the right, for those who have previous experience with building PCs, you will see this as a computer chip. This is exactly what a ASIC is. One of the attacks that I kind of want to talk about and what the research is kind of based around is called optical probing. But what exactly is optical probing? Optical probing is a type of attack that uses specialized lasers to non-invasively extract information from a chip's electrical activity. So if we kind of go back here, this is can be perceived as electrical activity for the circuits. We kind of go into it a little later, but look at these purple parts. What if these purple parts indicate a pattern? And the pattern, and this is just say for example, this specific pattern is the pattern in order to encrypt your data while sending it over text. Given optical probing, I could use a laser to non-invasively extract the information from the electrical activity and reverse engineer. So let's say I want to take your data now. Let's reverse engineer that electrical activity to turn off this encryption. So by kind of analyzing how the light reflects off the transistors, attackers can map an internal chip operations without leaving a physical trace. Optical probing attacks, or no, other known as OPAs, are extremely dangerous as they can compromise sensitive data such as encrypted keys while maintaining nearly undetectable. And we'll kind of go into later. You don't need a literal laser. You can simulate a laser attack as well. So what exactly is the defense? The defense is dummy transistors. As you can see below, though transist the middles are transistors, and these transistors show the electrical flow throughout the chip. So in terms of like the hierarchy, you can think of this. ASIC is probably the highest point, the top of the pyramid. And as you kind of go down and down smaller, you get into transistors, is where the electricity flows. Yes. So in the middle, these are working transistors. These are the actual transistors the electricity flows through in order to function. The purpose of a dummy transistor is a non-functional component added alongside real transistors. Even though it is a dummy, it can mimic electrical and optical behavior of real transistors. But why? The reason we do this is because we want to make this visual noise in order to confuse and mislead those who are using optical probing attacks. And this is all measured through a metric called RCV. RCV means it stands for reflective contrast value. It is the amount of light that is bounced off a transistor in order to show the attacker how much electricity or heat is emanating from that transistor. Going back to the example, we could see this as sort of an RCV. You can imagine these purple parts may reflect higher RCV, as in more heat, more electricity, and this could be the pattern. Yeah, but dummy transistors are dummies that are placed alongside or around in the chip. But there's actually a few approaches. We actually explored one of those approaches right here. One of the early approaches was something called random placement. These random placements allows us to place dummy transistors across the layout of the chip to, in order to create this noise. However, the results were unreliable as the attackers can spot the real transistors fairly easily, even due to noise patterns. As you can see below, the left is the original design. The right is our modified design. Um, of course, when you based on first look, you can probably assume that most of them are fake transistors, uh, due to the fact that other than the transistor on the top, these transistors are different. So it may indicate like, yeah, these are the real transistors. When we were doing random placement, we were testing through um, many types of numbers and transistors, whether it's left, more right, but it was kind of truly random. The only constraint we had was these dummy transistors weren't allowed to overlay on the real transistors because that causes problems when this is implemented in real life for manufacturers and the functionality of the chip. So how did we combat this? So currently, right now, the research is kind of wrapping up. We but the approach that we kind of laid upon was this redefined approach. It was called strategic placement. This like placement and the strategy of placement uses dummy transistors, but is not random. So basically, it takes the real transistors and we place dummies on the left and right of the real transistors. However, there's a measurement to it. Uh, as you can see in the slide, we measure based on these units. These units may depend towards chip, but this is generally what we use. In our case, millimeters. That is the metric that we use. Currently, right now, there is a machine learning approach using random forest regressor as currently being developed and tested in a simulation environment. In which, so given, in this particular case, in this ASIC, this is a ASIC or a chip known as NAND2. It's more of one of the more simple and basic ones in the community, and used for using our random forest regressor model. We're hoping to, in order to every time we get any chip, whether it's a NAND 2, whether it's a inverter, or whether it's a much more complicated chip, we can reproduce the same results given our strategic placement with these in mind, with the measurements in mind. Um, yes. So currently, right now, we have this NAND 2 case, with the original being on the right and the modified on the left. Currently, right now, it's not up to scale, so note that. And currently in the modified designs, these darker transistors right here are the originals, with the more lighter shades being on the left and right of each transistor being the dummies. Currently, right now, we do see a change in RCV, which is promising. Uh, what we need to kind of determine is this change in RCV insignificant enough to cover and make this noise that we were kind of talking about earlier? And that is something for us to be determined. Our next steps is kind of to make a heat map and to compare different designs, different nanotubes, and different inputs with our dummy transistor placement to truly see if we are covering and making this noise in order to make it more difficult. Once we have this, we'd love to pass this on to anyone in the community, anyone in the industries who will be interested. To wrap everything up, we start to explain the importance of ASIC and how they're increasingly being targeted by these optical component attacks. We looked at the limitations of random dummy transistor placements and proposed a smarter defense, hopefully using machine learning models. Our planned approach is to use RCV in a combination with a reinforced regressor model to determine where it's best to place these dummy transistors for maximum protection. Currently, this effect is being tested in simulation. Our next step is to test it with bigger and more industry standard ASICs. Thank you for watching. I look forward to your feedback and see you soon. Thank you.